In the previous video, we saw sleep sort, which cheats by putting the answer at a specific place and time so that it's waiting for us. So what we're going to do now is exploit space instead of time. So we're going to use an array to be able to put the answer where we need it to be. So let me give you an example. Let's suppose we have here a table of a bunch of information, and we have a bunch of keys. So each of these you can think of as an object of type, I don't know, row or something. And each key has a unique integer from 0 to 11. Now let's suppose that we want to sort by the key value, this number. So the idea here is we're going to create a new array of the same length, and then we're just going to copy the item with key I into the ith entry of this new array. So for example, we have Sandra, who likes presumably vanilla ice cream, and Grimes. Okay. So what we'll do then is we create a new array, and we say, Sandra, you're in the wrong location. You should be in location 5. So these array entries are 0, 1, 2, 3, 4, 5, and so forth. So we copy over Sandra, vanilla, Grimes, and 5. All right, here comes Lauren. Where's Lauren going to go? Top row, because Lauren has it key 0. Okay, how about Lisa? Where's Lisa going to go? Well, in the last row, that's 11. How about Dave? Dave's going to go at 9, and the same process will repeat, and we end up getting all of our items sorted. So here what we do is, because we know exactly where the item needs to go, because we have an index number, we are able to just throw the answer into the appropriate place. And it's kind of like sleep sort in the sense that rather than waiting 11 seconds for this row to get printed out, we put it in position 11. So it's the exact same idea. Now, unlike sleep sort, there's no weird catch here. This one just works. And we think about this runtime, well, it's just going to be in time, right? I mean, for each item, you copy it to its appropriate array location. And each of those takes constant time. So we just sort it in items and theta in worst case time. So what do we do? How did we avoid the proof from puppy, cat, dog? Well, we didn't use yes, no questions. We didn't do any comparisons. We just said, your item 6, go in location 6. That's not how puppy, cat, dog worked. Remember, puppy, cat, dog was you have boxes, you can't look in them, you can only weigh them using a scale. Our model of computation in that case was based on comparisons. Here, it's something else altogether. So this is the simplest possible case of what is known as counting sort. This is a real sort that people really do use. And in the version we just saw, it required that our keys be integers between 0 and n minus 1. Now, there's more complex cases that we're going to deal with in the coming videos. It may be the case that the keys are not unique. Maybe you have 2 4s or something. It may be the case that they're not consecutive. Maybe we have 0, 1,000, 6, 94, whatever else. It might not just be a consecutive range. And we'll also see that we may have non-numerical keys. So this will also work even if the things that we're looking at are not numbers. But that is the heart of counting sort. And in the coming video, we will explore this and make it more general than this case that's between 0 and n minus 1 with integer keys.